minash-shaytanir rajim. Bismillahir-rahmanir-rahim. Qul huwallahu ahad, Allahus samad, lam yalid wa lam yulad wa lam yakul lahu kufuwan ahad. So, good morning to all participants at the second day of the workshop. And we would like to welcome all the participants who joined this morning, and will be joining some participants later on. So we will start with the workshop. I will request Professor Zidin to start your presentation. Professor Zidin, now you can share your screen.
Sorry, Professor Jijin just told us that her network has something wrong, and she is connecting now.
Okay.
She says sorry, and I need a couple of time.
Back. I'm back now. Back again. So, I don't know why my computer just. So I need to reopen my file. Share the. Start. Share the screen. Can you see the screen?
Yes, yes.
Can you see the slides? Yes. Okay.
Yeah, 放映.
I need. Yeah. Oh yes. Here. 放映不了。
对，没有作用。
刚才呀，
那个再重新换一下那个演讲者模式，您往上看有一个切换显示模式。
切换
显示。
行了吗？
可以了。
可以了哈。Okay, good afternoon. Yeah, let's start the second day, the workshop of the second day. And I include my email here. And yeah, this is my email. If you have any questions, you can write email to me to ask. For example, if you like, ask some questions, you can email me. And then also yesterday I have introduced them. And then the agenda yesterday we introduced these two parts, and then today we will talk about the problem frame approach. So we start from the problem frame. Then when we talk about the problem frame approach, we need to introduce you the Professor Michael Jackson. Because he invented the problem frame approach in 2001, and he published a book on problem frames, yeah, in 2001. If you would like to know more about the problem frame approach, you can read this book, and this is the source of the problem frame. Then we going on to the course, the overall of the problem frame. First, I think we need to yesterday I mentioned that the tasks of the requirements engineering is to identify engineering is to identify the problem and to locate the problem, to build the description of the problem. This is the first three main steps for the requirements engineering. So here there is a question: how to do what we need to do to identify, to locate, to build. From where we can find the problem. Yes, we can give you a illustrative picture to show where is the problem and where is the solution. And in this picture, this part is the computer and the software that install in the computer. The computer the software is the solution here. But where is the problem? This part, the right-hand side of the picture shows the real world. Yeah, yesterday I have also mentioned that the problem comes from real world. In real world, you can have different things, and we can see around of you, and you can see what is in the real world. And from there's if you want to let the computing system to know the real world, you need to many modern techniques, like many modern sensors, actuators. They are becoming the bridge between the real world and the digital world. Somehow we call the software world is a digital world. It means because the software can only deal with the need to be deal with the digital information. So this information. So this is a illustrative picture to show where is the problem. And when we do the requirements engineering, we need to design a solution on this end. So this is a problem end. This is a solution end. So this is a very high level general ideas about the problem. And then how to locate, because the real world is a huge, big, and everywhere. And how to locate the current problem you are facing, how to describe the problem, how to decompose problems, and how to derive software requirements specification. According to in the problem frame approach, they tell you. Give you the answers about these questions. Let's start with an example. A small house. This is a small house. Yeah, this real world. Many rooms. The people lived in, and there are lots of like cars, tables, window, and doors, and other things. There are lots of things in the real world. And also, if you want to build a smart home, then you need to have many sensors and actuators, like wearable sensor, and like a screen, like a computer screen to show the information, and also the temperature sensor and the light sensor, etc. So they have this infrastructure of a smart home. but only if you only having the infrastructure is not enough. Is not a smart home, because when we say a smart home means this home can know you and can feel your desire and do some operations for you. So we need to let this home with many devices to become smart. So we need to, this is the motivation for developing software. Yesterday I mentioned that what drives you to develop software. First, at the very beginning, you need to have a motivation for develop a software. So let the home become smart. That is a motivation for develop software. So with this motivation, we started to locate the problem, how to make the home smarter. So we located the problem. I mean, I have mentioned that the problem is from the real world. So we identify the entities of the real world. I just assume the problem will come from these real world entities. And with these sensors and actuators, we know, the computing system may know the real world with these sensors and actuators. So from this aspect, we just say, oh, the motivation of the developer software is letting the home be convenient, comfortable, and safe. And what we mean to let the home what we mean by the home being convenient, comfortable, and safe, we can ask and we can discuss with the stakeholder. Oh, they may tell you something like this. Oh, turn on the air conditioner when the temperature exceeds 30 degrees. When no person is in the room for more than 30 minutes, the equipment return to their original states, all the equipment. And I'll turn off the lights and pull the curtain when the inhabitants go to bed. This. Open the window when the inhabitants wake up in the morning. Close the window when it rains, etc. The users, the stakeholders may tell you these kind of things to say what they mean. A home is smart. So with this kind of desire, and we can start to locating the problem, and so we elicited the entities in the real world related to the descriptions about their desire. Located. For example, the air condition in the description of their desire, they mention the air condition, and they mention the window and the curtain, and they mention the other things. Wake up. We need to have a sensor to detect the inhabitant is wake up. Like they mention the safe. This alarm for if strangers getting closer to the home, the alarm should be loud, should be sound loud. So this is the first step is identify the entities in the real world, and then you need to have include some sensors and actuators to feel, to sense the real world entities, the state of the real world entities. So you need to include the sense. And then the software, the smart home software should be here inside. Because they needed to use these sensor, the devices, to detect the states of the real world, and also comments may take effect through the actuators. So the software is located here. So this is just, I mean, location of the program. And where is the program? So we need to get more information. For getting more information, we need first to write the context. Let's give you a context of the software. Before we can get in more information, we need to describe precisely about the context first. And in the problem frame approach, Michael Jackson invented a diagram, or this is just to show what it means the problem context. Yeah, but let's, we just abstract the ideas from the original picture about the smart home. The software to be developed is here. This is a machine, computing machine with a software, and the entities of the real world is here. That will become the environment of the software. This is the problem domains. And there are lots of sensors and actuators here becoming the interfaces between the software and its environment. So that means the environment of the software serves to locate the problem and become the boundary of the problem. The boundary means all the entities we have identified in the real world becoming the boundary of the software. Yeah, this is the idea. And with the concept of the context, problem frame gives the context diagram. A context diagram should show the parts of the world where your problem and its solution machine are located. Yeah, this is the context diagram should serve to describe the part of the world. And also the interfaces by which those parts are connected. So the purpose of the context diagram is describe the part of the world and also the interface. For letting us draw the context diagram, they have some more elements we can use to make the description. For these three, in the problem framework approach, they call the domains, the code domains. And this kind of rectangle with a double line here, there's a machine domain. Yeah, using this element to describe the machine domain. And these two rectangles, one is just a plain rectangle and one with a single line here. They are problem domains. Yeah, this one also called is also called the given domain, and this one is called desired domain. And for describing the interface, there are three kinds of interface. The event interface, that means from this link just want to capture the events happened in the real world. The state interface means this sensor can detect the state of one element in the real world, in the one elements of the real world. And also the value interface means it serves to input and output the value, the numbers means all the other all the characters, only the values. So these three kinds of interface. In program frame approach, these three are also called shared phenomena. That means domain and another domain, there's interface between them, can link them, and through this link, they have some shared phenomena transfer happened in the interface. Shared means these phenomena can be are shared by these two domains. So that is meaning of the modeling description elements. Let's see an example of simple context diagram. This is a context diagram that shows the light controller. So the machine domain is a light controller, and this problem come from two entities. The one is the switch operator. That means the switch, you can, through the switch, an operator can operate on the light, can operate on light through the switch. And also this one is a light unit. That means, you have a light. You have a light set or something. And this controller is, can accept the comments of the switch operator and send the send the comment to the light unit to make it turn on or turn off. So they have two interface. One is between the light controller and the switch operator. The other one is light controller with the light unit. And the phenomena shared by them can be written like this one. This is on the switch. You have an on button and have an off button. So you have two buttons in the switch. So this phenomena shows switch operator can control on button and also control the off button. And this phenomena can shared by light controller. This interface means this one. And the B interface means the LH means light controller. Light controller can control an on pulse and off pulse to the light unit, send a signal to the light unit, send these two kinds of signal to the light unit to make the light on and off. And this phenomena, I think there's a common column here. And this phenomena means light unit can show its states. Yeah, when you turn on the light will stay in the state of on. When you turn off the light will stay in the state off. So this light unit can control state on or off back to the light controller. So the light controller can know the states, current states of light unit. This is the meaning of the context diagram. So here, this is the system, the software system we were developed. And these two are the problem domains and the boundary of the program. And these two are the interfaces. Yeah, this the meaning of the context. And these are phenomena shared through the interfaces. Yeah, this is a idea about the context diagram. And then we can, I want to ask the teaching assistant to show and guide you to use the tool and the domain and use a tool and to learn how to make the context diagram. So let's ask the teaching assistant to open the tool. I need to I needed to let you to share the screen. So I ended this one. Oh, yeah, no. Where? 啊，停止共享。OK。
Now can you see a web browser? Please open a web browser. Okay. And please open a web browser and input URL http re4cps.org and click Tools. Choose these tools. Wait some minutes. Okay. Have you followed? Just post the URL and find this tool. Okay, now start a new project. Click New button and import the description. Let unite and your personal info. Then confirm. First, identify the machine. Click machine icon on the left bar and click on the graph. Double click to edit. Import description. Let controller. And short name LC. Then confirm. Click next button on right bar to enter next step. Identify domains. Click domain icons on the left bar and click on the graph. Then double click to edit. Okay. Then import the description. and short name SO is a given domain, and its domain type is visible or confirm. Similarly, we get the second domain, import description, let unite. Short name is LU, and its physical property is given domain. Domain type is causal. Then confirm. Okay. Click next step to identify interactions. Click interface icon and click on LC and SO. Then interface A will appear between LC and SO. Then double click to edit. And phenomenon between LC and SO. The initiator is SO, and phenomenon is on button. The type is event, and similarly we can get the off button.
Now we get two phenomena here.
Similarly, we get the interface between LC and LU. Double click to edit. We change initiator to LC and phenomenal on pulse. The type event big and similarly, we can get off. We get 4 phenomena. Then confirm. We can see the information of context diagram. Okay. That ends.
Professor Jin, you can stop.
Professor Jin can start.
Oh, yes, yes, I will start to share my screen. Eh, 这是对的吗？ Can you see the screen?
No, 看不到。
No, 看不到。
No.
No.
它是
How about this? No. Let's still cannot. Oh, how about now? Can you see? Can you see the screen?
Yes, yes.
Oh, yes. Okay. So let's start. Let's start. Then we move on. 诶，
切换一下那个演讲的模式。
哦，还要切换？可以了吗？
可以了。
啊？
可以了。
可以了。Let's move on. So the TAs has showed the tour, and the next is exercise. Please, can you try to join a context diagram of the smart home system? Yeah, this in the right-hand side, the sentences show tells you what were, I mean, what entities they were related to the problem. Can you try to think about it, to identify the entities from the real world and identify the interface between the real world and the 2P system. I will let you think about it and draw part of it. I mean, give you 5 minutes to do that. How about this? Okay. You can think about, and then you.
I would like to add something. If you are not follow whatever side by the TA, you can see the examples in our website and follow these examples. We have demos, and you can see the demos there and try to figure out how to draw a context diagram.
Okay. Okay. Yeah. Have you had an idea about have you got an idea about the context diagram? I think many of you used the tool, to learn how to draw the diagram. Let's move on. Yeah, for the exercise, the smart home. This picture show partial of the diagram of the context diagram of the smart home system. And you can see, yeah, for example, in this part, the coffee machine, the toaster, weather system, and the kitchen robots has appeared in the description, or in the stakeholders description, users description. So they are from the real world. So we identify them to be the problem domains. And also this side the same. And you may ask why the user, of course, from the real world, and also else from the real world, why they are not direct linked to the system, because the system cannot directly link to them. They need to use sensors or display systems to link with the users. We model the sensors and the display system because we need to detect the behavior, the state of the sensor, and also using the display system to show the information to the user. So they are functional device. So we need to capture this. And in problem frame approach, this kind of problem domain is called the remote domain. Yeah, this kind of remote domain. So this is the context diagram. So next, after identify the context, after drawing the context diagram, we have already identified the environment of the software. So, but I didn't mention what kind of problem the software need to solve. We only mention which kind of devices the software can interact with. So next step is a problem description. Also, for the problem description, in problem frame approach also invents another kind of diagram. It's called a problem diagram. Compared with the context diagram, the problem diagram includes the requirements in the diagram. So that's also, we just use, they also invent some modeling elements. They use this kind of elements to describe, to contain the requirements. Yesterday we have mentioned to you, and requirements is some kind of conditions on the system will satisfy. So this the requirement describe the conditions on one or more problem domains, and the requirements. We have two kinds of requirements. The first one is the requirement reference, and the second one is requirement constraints. From their name, we probably can capture the meanings. For requirement references, just I mentioned a phenomena from the real world. I just mention it. Don't constrain it. Don't not desire it. But if they happened, means that means if they happened. And the second is requirement constraints. you can see from the constraints, that means you want to the phenomena will happen. That is a difference between the requirement reference and the requirement constraints. So the meaning, yeah, it's take the this is just mention the phenomena that will happen in real world, and this is for ask the phenomena will happen, need the ask for the phenomena. So this is the three kind of modeling elements for the problem diagram. So yeah, this is the meaning. The reference means if it is happen like this, and this constraint, this is asked for. So this is the difference. And then we can show also the light control from this part is from the the context diagram. These three domains come from with the interface come from the context diagram, and for the problem diagram we include requirement here, and one requirement reference and one requirement constraints. So these requirements, this program means commanded behavior. That means when you push the button of on, push the on button, when the operator push the on button, they need the light change their state into on. That means this is a constraint. So, and for the interface, we still have A. A means the operator push on button or push off button. Yeah, this A, the same phenomena, same interface. And the B are also not change. And the C, the constraints, requirement constraints, yeah, they can capture the state, the light unit, the state of the light unit. That means they can they ask for the light unit in on state or in off state. So this is the interface between the requirements and the problem domains. So that is called the commanded behavior. That's the requirements. And this is the conference requirements reference and requirements constraints. Okay, another slots for showing the tour. Let me stop the screen sharing. Move to the TA. TA, please show your screen.
Now we start to draw the
On base of the context diagram on the same web page, you can still use your context diagram, and we now go on to get a context. Can get a problem diagram.
Okay, and then identify the requirement.
Double click it.
Input the description, commanded behavior. Then confirm. Now get the requirement commanded behavior. Click next button to identify reference. Click on the reference icon on the left bar and click on switch operator and commanded behavior. Then we get the reference C between SO and commanded behavior. Double click to edit. Um, Different from identify phenomenon on interface, we need to choose whether the phenomenon is constrained or not. Some phenomena have appeared in the interface. We only need to select from the list and do not to identify the initiator and the receiver, such as on button. After choose this phenomenon, we only need to click and button, then the phenomenon will appear in the phenomenon list. Similarly, we can get the phenomenon of button. Then we get two phenomena. Then click confirm. Next, we will identify the constraint between let unite and commanded behavior. Double click to edit. The phenomenon is on and click and button. The type is state is similar with the phenomenon in the interface and off. Then we get two phenomena in the phenomenon list. Then confirm. We can get another requirement, such as the light can be turned on or off regime. We can click back button to enter the step or identify requirements. Click requirement icon and double click to edit. Import the description. Let regime. Then confirm. Now get another requirement, let regime, and we click next button to identify the reference and constraint. We add a constraint between let unite and let regime. Then double click this and add phenomenal on. Click and button, the phenomenon will appear. Similarly, we can get the off phenomenon. Then confirm. Now we can get the problem diagram of light controller. We can click next to we can see the reference phenomenon will appear in this. That's end. Okay, I'll turn to console.
Professor Jin and other students can practice.
Yeah. Yeah, let's practice the drawing the diagram, drawing the problem diagram. That is also the smart home example. You can start to practice. I think I can give you 10 minutes, right? Okay. Okay, how about the practice?
Yes, it's fine. You
Yeah, it's fine. Proceed forward. Okay, so I can show also part of show also the problem diagram of partial problem diagram of the smart home system. Yeah, you can see from this picture, from this diagram, this part is a context diagram. Yeah, this part contains the rectangles, all the rectangles, the context diagram. And based on the context diagram, we can include the requirements. In this picture, we include the two requirements. This is the first and the second. Yeah, if you have more requirements, you can include more. So for the first requirements, first requirements means in the morning prepare the breakfast. So it's need using the coffee machine, the toaster, and also the related to coffee machine, the toaster, the kitchen robot, and also some sensors. And the second requirement means display weather and air condition. So that these requirements related to the display system, the weather system, and also the air condition. So display the weather, and also you need to detect the weather. So this is for detect the weather, and also this is for detect the weather. So where is the air condition or display air condition? So display air condition here. Detect the weather, air, and get the information from the weather system and display on the display system. So this is the second requirement. And for each requirement, we need to describe the phenomena between the requirement and the domains. So here you can see here the phenomena means the description shows the air quality, temperature, and the humidity. So that is one phenomena. And this is a requirement constraints. That means the display system have to show this one. Yeah, when the air have some phenomena and the weather system have some phenomena, the display system have to show this information on this screen. And that means that is the second requirement. For the first requirement, KLMN. K, where is K? K here. K means a coffee machine can be on state on or off. Oh, sorry, off. And L means toaster can be on or off. And the kitchen robot start or down. And the sensors, yeah, can sense the inhabitant if the inhabitant wake up. So that means if the person wake up in the morning, you need to put the coffee machine on, and also after finish, you need to put it off. Also the toaster, also the kitchen robot. That is for the second, the first requirement. We include in the context, based on the context diagram, we include the two requirements and also the interface between the requirements and the problem domain, and to build the problem diagram. So this is the first two steps for the problem frame approach. So let's finish the first part of today's workshop. We can have a break. How long do you want? How long do you want break for the break? I would like just 10 minutes break, and then we can start earlier and then finish earlier. How about this idea? How about this? If no objective, I think 10 minutes break from now.
Yeah, Sarah said 10 minutes.
Yeah, wait.
Hello? Ma'am, we can take a 15 minutes break. After that, we will start the session.
Off 15 minutes, okay. 15 minutes.
10 minutes. Okay.
No problem, 15 minutes.
All right.
Okay. Okay.
So I have some tea. Ma'am, you can also have some tea. We are also having some tea over here. Hello, ma'am.
Hello.
Welcome back.
Yeah, we can start now.
Yeah, you can start now.
Okay. Okay. Okay, I hope it's still morning. So good morning, and we go on with the second section, and we go on with problem projection. Problem projection. So what is problem projection, and why do we need to do problem projection? That's the first question we want to answer. So why do we do projection? I use this sentence to explain it. That is, the problem is too complex to be defined. We can see many examples here. The system is so complex. The smart city or even the smart home is too complex. So to deal with complexity, decomposition is necessary. Oh, sorry. And in the Jackson's book, it said in the problem frames approach, he proposed a kind of decomposition. It's called projection. So what is projection? Okay, we use this schematic diagram to show this. And this is a projection while this is a partition. And we can see these two diagrams, and the difference of them are the projections have overlaps, and A, D, C, B, they all have overlaps. But for the partition, we can see A, B, C, D, E, they have no overlaps. So projection means there are many overlaps. And as to our problem projection, we mean that we got a version or description of a domain or interface or requirement in which only those phenomena and properties are included that are of interest for a particular purpose in hand, which means that for a problem diagram, we just showed you, and the projection means to get a sub-problem. This sub-problem also has the motion, has the problem domain, have the requirement, have the interface, has the phenomenon. So, so the next question is how to conduct projection. Can we conduct the projection automatically? And we find that in relation algebra, there's a projection. It's like this. And from this, we find three aspects that must be clarified before you define a projection. They are, first is the project dimension. And the second R is the project object, means you project who. The third is the result, the projection result. So if you can define all this, then the projection can be conducted. So in our case, the problem lies in this. This is a problem we described in problem diagram. And these are the sub-problems. The sub-problem also in the form of problem diagram. So the problem is a problem projection object, and the sub-problems is the project result. But the difficulty lies in what is the project dimension. How can we project the one machine into many machines, and there are corresponding prodomains? How can we do that? And of course, these prodomains have overlaps, which means one prodomain may appear in many sub-problems, like an air conditioner can be controlled by human or can be controlled by time. So how can we find the project dimension? We propose that scenario can be a project dimension. And what does mean? What does scenario mean? This scenario will mean a meaningful flow of interactions between the system and the problem domains. And using this scenario, we can represent the realization of a requirement by interactions. And I don't know whether you understand or not. Yesterday, we talked about the use case. And you can see, actually, a scenario is similar to the scenario of the flow in the use case. And a use case is also can represent a requirement. So so basically, we are doing a similar thing by defining the scenario. Our scenario is normal with the other scenarios, and over this scenario, upon these scenarios, we can project. We can define problem projection, and the project object is a problem and the dimension is scenario. And we can follow the algebra projection and define it like this. This means the problem P could be projected using scenario, and because our scenario is related as a mapping to a requirement, so we requirement here, we the problem can be projected upon the scenario, and the result is a sub-problem SP. So this is our definition about the problem projection. How to solve the problem goes into how to construct a scenario, and we define for each requirement we construct a scenario. A scenario is an interaction between the environment and its another system. So this is the problem diagram of the light controller, as we have said. And we see that we find there are interactions. We call these are interactions. Sorry. These are interactions. The interface are the interactions, the interfaces are interactions, and these are requirement reference and the constraint. They are interactions too. So we define a scenario is according to the activity diagram, and we use each node to be an interaction here. This is inter3 with the interaction 3 on button. This means, and interaction 2 on pulse. And the flow is using the similar notation in activity diagram. So we can express all these, all the interfaces, but we class it in order to represent the requirements in realization. We also distinguish these two kind of interactions. We call these interfaces, because the behavior interactions, because it's describing the behavior of the machine. Here it is a light controller. And we call this requirement reference or constraint is called expected interactions, because they are what the requirements really are. They are what the users want. So in order to express how a scenario realizes a requirement, we also have the expected interaction flow. And moreover, we have relations between these two kinds of interactions, which means the behavior interaction will enable these expected interactions and make the requirements happen. So we define we define 5 kinds of relationships between the behavior interaction and expected interaction. For example, this green line means a synchronization, means they happen at the same time. For example, in here we got inter3, and this one is also inter3, which means we are observing that the operator, the switch operator, press on button. They are the same, so they are, of course, they are synchronization. And the second is the red line. And this red line means they have directions. This is from the behavior interaction to expected interaction. And we call that this is the on pulse enables the on state, which means whenever the light unit receives the phenomenon called on pulse, then it will be on. And this is domain property. And here we don't have the other, but we also define the others. From the expected interaction to the behavior interaction, which means this behavior interaction is expected by the expected interactions. It is a requirement enabled. For example, if you want to know the speed of the car, and this is what you want to know the speed of the car, then you ask for a device to measure the speed of the car. So you need a behavior to do that. So this is what you want, and the behavior. This is a requirement enabled. Besides that, these three are the relationship between the behavior interaction and the expected interaction. And that's the way we have decided that behavior interaction actually this is activity diagram and this is activity diagram. And this we call the behavior orders, and this is called the expected orders. So this is a scenario graph we get. It's quite different from the use case scenario, because use case scenario we have said yesterday is about it is written by text. Second, if we use scenario sequence diagram to describe that, it's also it is a sequence diagram. Here we not only describe the behavior, the order between the behavior interactions, we also have the expected interaction orders, and we also specify the relation between the behavior interactions and the expected interactions. So that's where we different from the other scenarios. And from this scenario, we can say this is expected interactions. This is what we want. This is our requirement actually is. And if all of them have behavior interactions, we think this interaction will happen. Then this we can describe how our requirements are realized. And similar, we have for each requirement, we can draw a scenario graph. It's like the use case, because the use case for each use case, we can have a scenario. We can have a sequence diagram. And for this, for example, we have two requirements here. First is commanded behavior. As we just said, it's according to the operator's command. The second is light regime, which means that you can ask the light unit to on or off based on time. You can say at 5 o'clock, okay, the light on, or on the 6 p.m. I think the light will be off. This is pre-defined regime, and this regime can be executed automatically. So they are different. For this light regime, we can see that, okay, on time, even it's on time, then it's on pause, then the light unit will on, and if we receive after some time. Sorry, I think that's something wrong with this activity diagram. We need to wait for some time, and then we put on pause, and then wait some time, we put on off pause, and then we can find that, okay, if you get on pulse and the light unit will be on, and if we get the off pulse, the light unit will be off. And so we get the second scenario graph. Okay, now let's turn to the very exciting part. Is about the projection, how we project upon these scenarios. Okay, and this is the scenario, the first scenario we get. And now we put this scenario according to this scenario. Okay, first we light controller, we can get a sub problem. We can call it light controller 2. First, I'll give it a last name. And the second is according to these interactions, these interfaces, we can get these interfaces here. And according to the connection, they also have their receiver, sender, so we get the problem domains here. And according to the right part, the expected behavior, we can get a requirement reference and a constraint. So we get a new sub problem. And this sub problem, we have a sub machine, and we have problem domains, we have requirement, we have interface and the requirement reference and constraint. So this is a new sub problem. So from a big problem, we get sub problem. This is according to the scenario 1. And according to scenario 2, we can also get another sub problem. This is how our projection works. And according to this, this process can be automated. So now let's say our tool, we also have a tool. It's called tool. It's here. You can now open this URL and try to follow our TA and use it to experience how our projection works. Okay. Now I open the main page. You can go to the main page. Sorry, I need to now you can open our homepage. Can you see our homepage here? Okay, and then you click the tools here, and now you find the problem projection, and click here. Okay, now ask my TA to do it step by step.
Hello. Now we can open the project. Click the open button and choose your self project. Click the, you can see the context diagram and problem diagram. Then click next to check the problem diagram. The diagram is correct. And now you can choose upload the ontology or not. Now we not upload it and draw the scenario graph directly. Click next. Now we can get the two signal graphs. Now we choose the first. First, we add the start, click the start and click the graph, and add the merge. Now let's define the relation between behavior interactions and the accept interaction. Now we choose the behavior enable and click the on pause and on. And then click the behavior enable and click the off pause and off. Off pause and off. Now we can add the accept order from the start to merge, and from the merge to on button, from on button to on. And we also can get the corresponding relation from on button to on pause. And we can add the also relation, the accept order from on to on button, from off button to off, off button to off, and from off to the merge. Now we adjust the position. Now we add the start and merge of the behavior interaction, the start, the merge, and add the behavior order from start to merge, from merge to on button, and from off pause to merge. Now we can choose the second scenario graph. Also add the start, the merge, the start, the merge, and add the relation from on pause to on. And the behavior enable from off pause to off. And as the accept order from start to merge, from merge to on button, from on to off, and from off to merge. Okay? Off to merge. And as the behavior order from off pause to merge, from start to merge, from merge to on pause. Now we get the two scenario graph and click next to finish your drawing, and then click next to check the correctness and integrity. Now this is the check the result and there is no error. And click next to check the well formed. Now the two scenario graphs are well formed. And click this, we can get the two sub-problem diagram. And then click the next, you can get the use case. That's all.
Okay, and okay, I want to specify something. create something because I didn't. Let's just still look at this too, and this context diagram and the problem diagram are actually from what we have just what we have just drawn. And this scenario graph is what you draw here. And from this scenario graph, we can see that first, I don't know whether you notice that these requirements on this diagram, we just describe the relation between them and the expected behavior interactions, which means if we press a button and we can expect that the light unit is on, and if we press a off button, we expect the light unit is off. This is what we expected. These are the expected interactions. And after we get to the relation between the on pulse and on, the off pulse and off, and if we put these behaviors between the expected interactions and these interactions between the behavior interactions will be automatically drawn, which means this can be derived automatically. So using our tool, there's no need to draw them by yourself. And the second scenario actually the same. And from here, and I want you to know that this on pulse and on the relationship can also be automated, and we will show that tomorrow. Because tomorrow the next topic is about the environment modeling based requirement engineering. That's also our work, and we'll show that later. And the second scenario, light regime, is actually the same. We use expected interactions to describe the relation between the between the behavior interactions. And the subproblem, you can see the subproblem. This is about the commented behavior, and this is about the light regime. And all these subproblems is according to the scenario graph. Okay, the last thing that I want you to memorize is that we have a lot of checks before we do the projection. Why do we do the projection? That's the next thing I want to share. But before that, I want you to practice. Would you like to practice this projection by yourself? Maybe I leave you some minutes and you can do it yourself. Okay, I just leave it here and you can do it yourself. And if you don't have your light controller problem to do this, and you can open others. And others is which one? You can open others. Open project, the light controller, and this one. This one, and you can open it and try to try to use it. I'll leave you some minutes. Okay. Okay. The use of this tool, this stop here. And if you are interested, and you can also find it have examples at our web page examples. And if you have any problem or question or some bugs, you find some bugs of the tool, please feel free to tell me. And now we okay. We'll go back to the slides, and I have other things to share with you. And as we just said that there are many checks before we do the projection. Why do we need this project? Why do we need these checks? Why do we need these checks? The question, this project, this checks is actually to ensure that the projected sub-problem is a complete and valid problem. Because you say, if we just get a scenario and we project it, but can you ensure that the sub-problem is a complete and valid problem? How can we ensure that? Because scenario is drawn by users. The users is uncontrollable. We don't know what he put. Just like the use case and the sequence diagram we draw yesterday. Do you know what you want to draw? And do you think your draw is correct? Do you think it's necessary? It is valid? No, it's not easy to ensure that. So we must make some rules to check whether how to ensure that. Here we propose a new concept. It's called well-formed scenario. This well-formed scenario, the purpose of the well-formed scenario is to ensure that the sub-problem. But how can we define a scenario, well-formed scenario? We want to define a meaningful scenario rather than a random interaction flow. So, and the another question is, what about the not well-formed scenarios? And before the projection, you need the strategies to make them well-formed. So this is a following task we need to fulfill. The first is define a well-formed scenario. Second, make strategies to make the scenarios well-formed. First, we define some well-formed scenarios. This well-formed scenario, actually, we give a very formal definition, but this is difficult to read. And we want that this can be included that there are actually two situations. The first, we want to the interaction scenarios complete. By complete, we mean that, for example, in this scenario graph, we got okay, this is expected expected interaction here, but we don't have any behavior interaction related to it. So, which means this requirement is this requirement reference or constraint is not supported by any behavior interaction. So it can't be realized. So in this situation means that the interaction scenario is incomplete. The second we found is the multiple rules, which means there's a problem domain and it may have two rules. One is a consumer and one is a producer. And for the different roles, he can initiate or receive different phenomena. For example, for the we define it as a static domain. For example, we think the static domain can initiate or receive the invariant state or share the invariant state, but the dynamic domain, we think it receives values. So from this phenomenon, we can check whether that the domain that it has both dynamic and static roles, just like producers and consumers. It is better to separate these multiple roles. So after this well-formed scenario, we can formally define the projection. We have different projection projectors, and for the domain, for the machine, for the interaction, for the requirements. Okay, the second big problem is for scenarios that are not well formed. We need strategies to make it well formed. How can we do that? And according to the questions, the first is there are multiple rules. If there are multiple rules, and we can introduce a model domain and to to separate the dynamic and static rules. And the strategy 2 is about the missing interactions. If there are missing interactions, and how we include, what we want to include the missing interactions. This may need to introduce new problems. Let's see some examples. And this example is a very benchmark example in Jackson's book, and also many papers in problem frames. It's about the package router problem. The package router problem actually is about a package router. The package router is a large mechanical device, and it is used by postal and delivery organizations. And it is to sort packages. This is packages, and we can use this router to sort these packages, and according to their destination, and they are sorted to different bins, and finally they got it. So the problem is to build a control machine, and the first is to obey the operator's commands. The second is to route the packages to their destination bins. And the third is to report misrouted packages. So from this description, we can get an initial problem diagram, and we can recognize a router controller is the machine to be built, and the package conveyor, and the router operator, package and router and display unit is the problem domain, and we can identify 3 requirements. Firstly, obey operator's command and routing correctly, and report misrouted package, and other behavior interactions and expected interactions. And for each scenario, for each requirement in the problem domain, actually we can draw a problem diagram. Like this. This is about route operator and the package conveyor. Sorry, I don't know what happened. And we can see that first, if the operator press on button, and the router controller will receive on say, and the package conveyor will be running. So we can get this on button, and on-say then running. So we got this. And similarly, we can get the off button, then I got stopped. So they're similar. This is about the first requirement. And similarly, we can get the other requirements, sub-requirements about the correct routing and the report misrouted package. And then to ensure the correct projection, we need to check in. And it turns out from these scenarios we found, first, there are missing interactions here. And second, we found there are multiple rules here, package and the router. This domain have multiple rules. It is dynamic and static. So for the missing interactions, interaction 18, and we find it's in scenario 2 and scenario 3. They are all interactions 18, right? Yeah. And to make it happen, actually, we need to introduce new domains and sub-problems. To make this interaction 18 happens, we need interaction 22. And interaction 22 means to read the relation between destination and B mapping. And this could not be provided by existing proper domains, so we need to add a new proper domain called destination bin mapping (DBM). And this domain is if it is this domain here, but where does this domain created? Which means this is the consumer, but where is the producer? Where to produce a DBM? So we have to create a new problem for editing the DBM. And for editing the DBM, actually, we can get a new scenario. It's called addition bin mapping. And for the second problem is the multiple rules handled by PR, which means this proper domain have been both dynamic and static. And by dynamic and static, how can we find it? We find that it is a value phenomenon and also an event phenomenon here. So package and router actually assumes multiple rules. So we need to separate it. How to separate it? Okay, I think we include the new domain as a model domain, and this domain can be used. We separate the packet and router. We got second router. One is the producer and one is the consumer. So we got a new we got a new ILM as a package router. We got a domain model package router here and separate them in two different scenarios. So the result is we got a new router layout model. And then we got 5 scenarios, 5 requirements here. This is a whole problem domain diagram, whole problem diagram. And after projection, actually, we got 5 requirements here. 5 requirements here. And now I want to show you our demo about the whole process. And as I don't know why the queue is quite slow, so I will, sorry. I will show our demo in my home. Sorry, I will change it. Sorry. Share my new. Wait for a minute. Yeah, this is a demo we have recorded. And now we can see the whole process. First, we upload all the and all this project and find it. Oh, sorry. Oh, sorry, it's not the same. Sorry, this is not the correct one. I don't know why. Sorry, I try to find. Sorry. Okay, it's okay now. Here we can find that this is a problem diagram, and we found this. We download it and to draw the scenario graph here. Okay, this is a new, and then the second, the third, and check that, and we find the question problems, and we give this strategy, and then we use a problem diagram to add new interactions here in 22, interaction 22 and 28, 26. And now the scenario is complete. And add a new scenario here. This is the requirement for editing. And then we check it again. Okay, now we found another question about the multiple rules. And then we start to update the scenario again. This is the version, and now we get five sub problems here. This is the whole projection process, and this process is actually we need to update the problem diagram and the scenario diagram at the same time. So sometimes we need to use the first two. So that's the whole process. Okay, and now we're back to the slides. Okay, about the problem projection, I'll share all this, and hope if you hope you are interested. And our tool is still developing, and if you find any bugs, please feel free to contact us, and you can find our email on the website. Thank you. Okay, the next week we'll go on with the last part. It's about the basic problem frames. The basic problem frames. Actually, why do they have problem frames? Actually, it's like, I think it's like the design pattern. You know, design patterns. Design pattern is at the design phase, but what about the requirements phase? The requirements phase, we have problem classes, which means that can we use something to define these problems are different? Are the requirements different? For example, the patient monitoring, the smart home, the library and administration, the weather display, the home heating. How can you character them? How could you distinguish them? You just say they have different names. So how to define them formally? We can say, so projection proposed this thing is called problem frame, and it defines an intuitive identifiable problem class in terms of its context and the characteristics of its domains and phenomena. So the first is, how can we characterize all these problem domains? So first he classified all these domains. He gave 3 domain types. The first is Carroll domain. The Carroll domain, it's like a light unit. You can see that this its property include predictable causal relationship among its shared phenomenon, which means the on pulse will enable the light will be on then. Whenever you receive the on pulse, the light will be on. It can be expected. Of course, maybe someone says, oh, what happened if there's an accident? What happened if the light is it's something wrong? That's another thing. It's whenever we think there's a pulse, we can expect the light unit will be on. If it doesn't, then something must be wrong. That's about the reliability. The device is failure. That's another thing. And the second type is a bindable domain. This domain is used to describe this who is physical but lacks positive predictable internal causality, which means these things couldn't be controlled. This is most of them are people. These people are uncontrollable, but you can't expect someone comes, you can't control anyone to go east. You can't expect its behavior. So this is a bindable domain. And the third is about the physical representation of data. It's called the lexical domain. We use X to describe that. So for each domain, we have C, B, X to characterize it. And except the domain, actually the phenomenon can be classified too. And we just said a phenomenon can be a state, event, and value. And by event, we mean individual happening. Each build, for example, insert a car, it is indivisible and instantaneous. The second is the value. And this value is an intangible individual, and it is not subject to change. For example, X, 15. And the third is a state. Actually, the state is a relation as we have defined in the state transition diagram. A state, actually, it is a variable in the values, a relation between them. For here, we think that only the chiral domains have state. So we get state is a relation among chiral domains and values. It can change over time. For example, the room of the temperature. Maybe it's over 40, it's lower than 40. That's changing, maybe. And all these phenomena actually can be classified into larger categories. They are chiral phenomenon. We use C to indicate that. So events or states indicating the entities. And the second, the symbolic. The symbolic phenomenon, we use Y to express that. It's the values, it expressing the values and truths and states relating only values. So we all use this. These are the characteristics to define the problem domains, the phenomenon. And based on these characteristics, Michael Jackson defined 5 basic problem frames. And they are called required behavior, commanded behavior, information display, simple workpieces, transformation display. We'll explain it one by one. The first, we can see, the first is required behavior. Well, what does that mean? We can use an example to show you. The first is, we can see this is a coffee maker, right? Coffee machine. Okay. And when you, for example, when you get up at 6:30 every morning and you want to drink a cup of coffee and you want the coffee ready. When you go into the dinner room and you need it ready. So how can we do that? You can get the coffee maker can be timed, and at the time at some time it will start to working. So how can we do that in a software, and how can we describe it in a problem diagram? Yeah, this is a problem diagram of a coffee maker, and this we can call a coffee machine controller. And this is a coffee machine. This controller is to control a coffee machine and to make it make coffee at before 6:30. So the control rules, what happens to the control rules? It according to the control rules to control the coffee machine. This is the problem diagram. And to To make it more generally, we find that coffee machine is a chiral domain. It can be controlled, and its phenomenon has predictable relations. So this is a chiral, and we find the phenomenon here. The on pulse, off pulse is say, and the coffee machine is on or off. This is say too. So we found, okay, there's a software that is controlling chirality domain, and this phenomenon control chirality too. So we extract this and get a kind of problem. It's called required behavior, and it's just like this. Okay, we got a controller machine, and we have a controlled domain, and this is what desired behavior. And this desired behavior, they have a phenomenon. These phenomena are all chirality. They are say, and say. So this is what he defined as required behavior. This required behavior, the intuitive notion is that some part of the physical world here whose behavior is to be controlled so that it satisfies certain conditions. Certain conditions. What kind of condition is it's defined by the desired behavior. Okay, then the problem is to build a machine, build a control machine that will pose that control. This is called required behavior. Then a controller machine to control the controlled domain to satisfy some certain condition. This is desire, the required behavior problem frame. And this diagram, we have the character on it. This is say and say. We call it problem frame diagram. It is a kind of a problem diagram. You can see it like this. Okay, now you can do an exercise. It's about the timing air conditioner controller. The timing air conditioner controller. Actually, in the smart home system, we want to control the air conditioner by a machine, by a controller. And this controller will set the air conditioner to turn off at 8 a.m. and turn on at 6 p.m. So can you draw a similar problem diagram or problem-free diagram of the air conditioner controller? Is it? Actually it is a typical required behavior problem. You can just follow what we have said. And if you are interested, you can use the tool to draw it. I'll give you some time, a few minutes. You can start now. Use the first two to get the context diagram, then the problem diagram. But this is easy. You are not interested in the tool, and you can just take a piece of paper and a pen and to write it down, draw it by hand. Yes, you can down on paper. Using paper, just write it down. Okay. See it again. Okay. I mean that if you if we want to make, we want to develop the air conditioner controller, and this air conditioner controller, you want it to control the air conditioner on time. The time is to turn off at 8 a.m. and turn off at 6 p.m. And can you draw a problem diagram? Okay, now it's limited to time. I'm only we go on, and of course you can okay, I see you. Okay, good. I see you, Sarah. I see. Thank you. Yeah. Let's say this air conditioner controller, and if you are not following us, and I think you can join. You can practice at any time because of using our website. And if you have any question, you can write to us. And as this to the air conditioner controller, actually it's like this. Air controller is going to control an air conditioner, right? And it have a control regime. And this control regime is specifying at what time the air conditioner is on and at what time the air conditioner is off. So the B has a AD. AD is the air conditioner, controls or initiates phenomenon on and off. And the air conditioner actually is to give an on pulse or off pulse to the air conditioner to control the air conditioner. And when the air conditioner is on, then he tell the air conditioner controller. So this is a proper diagram of the air conditioner controller. And in this air controller, it is easy to say that, okay, this is a machine to be controlled, and this is a Carroll phenomenon. So this is actually instantiation or use of the air required behavior frame. You can understand it later. Okay, now let's go to the second problem frame. It's called commanded behavior. And we can use an example to show you that. And when it is hot, it is summer now, it's very hot. So whenever you go to home, you say that, okay, I need to open the air conditioner. So we want a commanded behavior controller to control the air conditioner according to the user's command. It's not according to the time you predefined, it's according to the user's command. And this command can be by many things. For example, you can use the remote control. You can use your mobile phone. We don't care what kind of things you are using. They are interfaces. We only says that where the source of the command is people, right? It's a user who gives the command, and then the air conditioner, the state of the air conditioner will be changed. So we can draw a problem diagram like this. Yeah, this is the air conditioner controller. This is a machine to be built, and this is the air conditioner. And you need the air conditioner to be on or off. So you want to turn on or off the air conditioner by a command. And so where is the command from? It's from the operator, the air conditioner operator. So actually the operator give a command, and then we can use the open or close to express the command, open command or close command, and then the air conditioner will initial pulse to the air conditioner to control its state, it's on or off. So actually, it's from the requirement side, we can say the operator says open, then the air conditioner is on. The operator says close, then air conditioner is off. So this is the air conditioner controller. But what we want to say is more than air conditioner controller. We want to say this is a kind of problem frame. It is said that people, a bindable domain, this B, bindable domain, and is controlling a Carol domain, air conditioner. So so software. So we got B, C. Then also we have found that the existing operator found event, the command of event E, right? And then the air conditioner, the controller sent phenomenon to the conditioner, and these are Carol phenomenon. And then the state will be the state here. The state here is also Carol. So this is E, this is B, this is C. So these characteristics, actually we can characterize the whole problem. This problem actually like you conform to the operator's command and to control some devices. This is called commanded behavior. And the commanded behavior frame is like this. To more generalize, we got a problem frame diagram. It's like this. This is operator B. This is control domain C. And this is the controller machine CM. And this is the behavior. These are requirements. And you have the event and the Carol phenomenon here. So if you it's this kind of situation, this is a commanded behavior. And also we can develop the solution part, which means how can the machine, the controller machine to do something, how to design it. That's the other part. But we can, in this, we can characterize this problem and call it commented behavior problem frame. And the meaning is that there is some part of the physical world, which means the control domain, and whose behavior is to be controlled in accordance with commands, commands issued by an operator. So this is commented behavior. And this problem is to build a machine. This is a machine that will accept operator's commands and impose the control accordingly. So this is commented behavior. And also I got some exercise, but limited to time. I don't think we have time to do the exercise. I will, actually it's used many times. It's about the light controller. The light controller actually is the same. It is follows a switch operator's command and to impose control on the light unit. So this is a kind of a commanded behavior problem. Okay, well, let's go to the third problem frame. It's called information display frame. The information display is just as we said in the smart home. In the smart home, we want to know the temperature, the humidity, and the air conditioner, and the weather. Anything we want to, it will be displayed here. So to draw a problem diagram, it's like this. Sorry, it's not a controller, it's a monitor, environment monitor. This monitor is to monitor the air, so the sensors and find it and to display it. We can display the air quality. We can display the temperature, the humidity, and on this problem diagram, we can say this is the real world, and this is the display. This display is going to display what the real world information. So sorry, this is not a B. Display is a C. I'm sorry, I made a mistake here. It's a C. Then the air conditioner and the sensor is also a C. It's a C. And this is C, and the display is a E, and information is a Y. Information D is here is Y. Y is the lexical, the values, so it's a Y. And B means you have give some comment to display something. So we got an information display frame, and this frame is about this. It's our real world. This is display, and this is the real world is a C, and the display is a C too. And the phenomenon, the information machine is a C, but this is E and Y. And the meaning is there is some part of the physical world about whose state and behavior certain information is continually needed, which means that you need to continually display the state or behavior of such information on the display. So the problem is to build a machine that obtains this information from the world and present at the required form. So this is the information display. Okay, the fourth one is about the simple workpiece. The simple workpiece is we use example to show it. For example, in smart home systems, there are many control functions. And these control functions, sometimes you need to set some parameters, which can maintain a control parameter table. For example, you can include in the equipments to be controlled, the control parameters, the time, etc. For example, if we control the air conditioner and the air conditioner turn on 10 minutes before 6 o'clock after work, and the indoor temperature is maintained at 630 degrees. If it's necessary, so it is necessary to design a control parameter editor to create and edit the control parameter table. So how to control this parameter? How to edit this control parameter? So we need to make a editor, control editor. This editor, we use this editor is used by a user. This user will import some operations, give some comments, and import some operations, and the control parameter will be designed. We will just set control parameter table. It's designed. So this is a designed domain, and so and the phenomenon we can see that A is import operations. This is an event, and this is also an event. No, this is event. This is Y. This is Y. Sorry, this is Y. This is the lexical, the values, the parameters as far as the values, and the B is the comments. It's a E event, which means, and this D is B actually. This B comments, so it's EY. So this is a simple workpiece. To generalize it, we can use it like this. User is a B. A workpiece is X. This is a domain to be designed, and this is Y. And if you want to return something, you can get Y. So this is the editor tool. Actually, it is to allow a user to create and edit a certain class of computer processable text or graphical objects or similar structure so that they can subsequently copied, printed, analyzed, and used in other ways. So this editor tool, this problem is to build a machine that can act as this tool. This tool is the editor tool, that simple workpiece. And if you have any problem, it's like this. You have B, you have X, you have Y, you have E, then this is probably a simple workpiece problem frame. Okay, the next one and the last one is the transformation frame. The transformation frame, let's use an example. Suppose there is a sports health monitoring subsystem in the smart home system. And this system is actually monitors each person's sports health in real time. For example, it can give the personal weight, walking kilometers, calories consumed, calories absorbed, etc. And a sports health analyzer can generate statistical reports to show the relationship between people's health and exercise every day or every month or every year. So how to build this kind of machine? So we need a sports analyzer, and what we got is you get a everyday sports record, and then you get a report. You want to get a report, and you give certain analysis rules. So it's like, okay, from this record, we got a report according to the analysis rules. And this is x, and this x are the data expression. So A, B, C, D are both y. So to generalize it, actually, it's like this. This is a transfer machine, and this is input. It's a kind of x. The output is also kind of x. And the phenomenon are all the y phenomenon, which means symbol phenomenon. And this analysis rules is actually the I/O relationship. So the transformation frame, actually, he said there are some given computer readable input files whose data must be transformed to give certain required output files. The output data must be in particular format, and it must be derived from the input data according to certain rules. So this problem and this machine is built to produce the required output from the input. So if you get this x, y, y, and you can get the transformation frame. Okay, that's the all the basic frames we have talked about. And this all these problem frames are very basic, and they are very easy. You can see that it is easy. But most of them are commonly happened in our daily life. So I think they are very important. And also, injection spoke, there are many variant frames. And you are interested, you can go on to read it, to further reading, to further learning. Moreover, there are others. For example, there are some composite frames. There are some frame concerns. As limited to time, I didn't mention that. And I hope everyone are interested. And as to summarize our lecture today, we have introduced the problem frame approach, and we tell you how to locate the problem using a context diagram, and how to describe the problem using a problem description diagram, and how to decompose the complex problem using a problem projection. And by projection, we mean that this sub-problem can be matched with the problem frames, which is the basic problem classes. And using these frames, we can directly mapping to the solution. That's what we want. And now we are still working on it. That's all for this today. And I want to use some time to do some reminder for the next lecture tomorrow. And tomorrow we'll still use laptop and computer. We all still use our tool, but we want tomorrow we'll talk about the environment modeling based RE. This will need environment model editing tool. This tool we use Protege. This Protege you need to be downloaded beforehand, which means you can download the desk Protege here now. This night, and install it before the lecture. And tomorrow we'll tell you how to use this package to edit your own environment model. And if you have any question, you can ask now. And today, I would like to thank you for attention and thank you for your cooperation. We can see you tomorrow if you have any questions. No other no questions. No questions. Then today is done. We finished the lecture.
Thank you, Sean,
Yeah.
for a wonderful lecture. We
Thanks.
learn a lot from your expertise with the example sessions and tools related to the exercises in very
Yeah.
brief and very comprehensive.
Thank you. Thank you.
We will continue tomorrow morning.
Yeah. Tomorrow morning. So it's still on 10:10.
Yes, today's session is end from your side.
I mean, by your side, it's still 10.
Okay.
Okay. So
So tomorrow morning we will start at 10 a.m. At Pakistan time.
okay.
And at your place, it's about 1 p.m.
Okay. Yes.
Yes. Thank you.
Thank you, Zijan. Thank you.
Thanks, everybody.
Thank you.
Thank you. See you tomorrow.
Thank
See
you.
you.
See you.